we're now going to take a look at a few applications of anti-differentiation. So the first example we're going to look at here is deriving the equation of motion for an object thrown upward or downward near the surface of the Earth. So suppose we have an object and we throw it upward or downward near the surface of the Earth from an initial height of s0 feet with an initial velocity of v0 feet per second. Now recall that the acceleration of an object is the derivative of the velocity function, or the second derivative of the position function. So recall that. So the acceleration is the instantaneous rate of change of your velocity. That's what this says. Also, the velocity is the first derivative of your position function, or the velocity is the instantaneous rate of change of your position function, said in another way. Alright, now we want to derive this equation that we've been using before. Now near the surface of the Earth, acceleration is constant. It is negative 32 feet per second, or feet per second squared. That's the same thing. Now what that means is, if you're standing on a platform, say, and you drop something, so it's in free fall, every second its velocity increases by 32. That's what this is telling you. So in 1 second of free fall, your object will be traveling 32 feet per second. 1 second later, as it continues to fall, it will pick up another 32 feet per second, so it will be traveling negative 64 feet per second. And so on. 3 seconds later, it will be traveling 96 feet per second. It picks up another 32 feet per second in its velocity falling downward. Now, to find the we want to find the velocity function first of our object. So if we use this equation right here, acceleration is the derivative of the velocity function. That means to find the original velocity function, we want to anti-differentiate the acceleration. So if we evaluate this, of course that's equal to negative 32 t plus some arbitrary constant c. Now notice the derivative of this, if we were to take this and differentiate it, we get negative 32. If we take its derivative, we get negative 32. So this is our velocity. Our velocity is one of these. We don't know what the constant is yet, but we'll figure it out. So from this, we have that our velocity is negative 32 t plus some constant. Now we need to figure out what that constant is. Well, we are told that the initial velocity is v0 feet per second. So that means at time 0, our velocity is v0. So we can use this to solve for c. So if we plug 0 in for t, and v0, whatever that number is, in for v, we get, and that tells us that our constant c is actually the number v0 that we're given. So c equals v0, and so therefore here is our velocity function. Alright, now we want to find our position function yet. Well, from this equation right here, the position, if we take the position function and differentiate it, we get our velocity. So to find our position function from this equation, we need to take its antiderivative. So if we evaluate this, we get, now the antiderivative of negative 32t is going to be negative 16 t squared. Notice if we differentiate this, we get negative 32t plus, and the antiderivative of v0, now that's just a number, so that's going to be v0 times t. Notice the derivative of this is v0, and then we have to add on our arbitrary constant c. So this is our position function. This is equal to s of t. But now we need to figure out what the arbitrary constant c is yet. Alright, well, just like we did up here, we are given that our initial height that the object is dropped from or thrown upward from is s0 feet. So we are told this, we are given that s of 0 equals s0, that number. Okay, so we're given that. So if we take 0, plug it in for t down here, and the s0 we put in place of this s, we obtain this equation then. So we get and of course all of this here is just 0, and we get that c equals s0, and therefore our equation of motion is and there we go. We have derived the equation of motion for an object thrown upward or downward near the surface of the Earth from an initial height of s0 feet with an initial velocity of v0 feet per second. And we obtain that by taking the antiderivative of our acceleration, and we did that. When we did that, we found our velocity function, and then we took the antiderivative of the velocity function, and that gave us our position function. Now note one thing about this. What we did was we derived the equation of motion for the English system. In the metric system, this is our equation of motion for an object thrown upward or downward near the surface of the Earth with an initial velocity v0 meters per second and s0 from an initial height of s0 meters. Now notice instead of negative 16 we have negative 4.9 here. That's because near the surface of the Earth the acceleration is negative 9.8, approximately 9.8 meters per second, or meters per second squared. And when you take the antiderivative of this twice, you're going to divide this by 2. When you divide negative 9.8 by 2, you get negative 4.9. Recall, just like we did previously, if you divide negative 32 by 2, you get negative 16. Well, when we divide 9.8 by 2, we get 4.9. So that's where that's coming from. Let's take a look at another example. So in this example, we're given that a car accelerates from 25 kilometers per hour to 80 kilometers per hour in 10 seconds. And we want to answer two questions. First of all, assuming that the acceleration is constant during that 10-second period, we want to find the acceleration of the car. And then second, we want to find the total distance traveled by the car during that 10-second period of acceleration. Now you notice that we want to find the acceleration in units of meters per second. So we have mixed units here. So the first thing we want to do is we want to put everything into common units. So we want to change 25 kilometers per hour into meters per second and 80 kilometers per hour into meters per second as well. So let's first of all notice that 25 kilometers per hour that's going to be 25. 1 kilometer is 1,000 meters, so 1,000, replace the word kilometer with 1,000 meters. And 1 hour is 3,600 seconds. And if you evaluate that, that's approximately 6.94 meters per second. Just evaluate that on the calculator and that's what you get. Similarly, if we replace the 25 with 80, we get that 80 kilometers per hour is approximately 22.22 meters per second. Alright, now we have everything in common units. Now let's start the problem. So what we have graphically here is that the car is traveling down the road, and at this moment in time, let's say it's traveling 6.94 meters per second, or 25 kilometers per hour. The driver steps on the accelerator, and then somewhere down the road, 10 seconds later, the car is then traveling 22.22 meters per second, or 80 kilometers per hour. And it takes 10 seconds to do this. So we want to find the acceleration of this car. Alright, now we're going to assume the acceleration is constant. So let's assume a of t during this 10-second period of time is equal to some constant. We'll call it k. Now we want to find this constant k. That's going to be our answer to part A. Now let's also note one other thing here. At time 0, when the driver first steps on the accelerator, the car is traveling 25 kilometers per hour, or 6.94 meters per second. So we're also given that the velocity at time 0 is 6.94, and then 10 seconds later its velocity is 22.22, so we're also given that v of 10 equals 22.22 meters per second. So perhaps we can use these two pieces of information to solve for that k. Well, in order to do that, we need to find the velocity function here. So what we need to do is take the antiderivative of this, because the acceleration is the derivative of the velocity. So if we're given the acceleration, to find the velocity, we need to take the antiderivative of the acceleration. So our velocity, taking the antiderivative of just a constant k, we get plus c. So we have two unknown constants here, c and k, that we need to solve for. So we'll use these two equations to solve for them. So the first one here, v of 0 equals 6.94, that implies that if we put 6.94 in for the v and 0 in for t, we get that c equals 6.94. Okay, so now we have that v of t equals kt plus 6.94. Now we still need to solve for the constant k. Well, we're also told that in 10 seconds the car is traveling 22.22 meters per second, so we put this in place of the v, and 10 in place of the t. And now what we need to do is just solve this equation for our unknown constant k. So take the 6.94 over to the other side, divide by 10, and what we get is this. So this equation implies that the k is equal to 1.528, and that will have units of meters per second squared, or meters per second. And so we found our acceleration during that 10-second period, and this is the answer to part A. Now we still have to answer part B. We have to find this total distance, d, traveled during the 10-second period. Well, so we need to find the position function now. So to find the position function, well, the position function is going to be an antiderivative of our velocity. So we need to take the antiderivative of this. Now our velocity, let's put the number in for k there, so our velocity is now we need to take the antiderivative of this, and we will get notice the derivative of this function will give us back our velocity. And we can clean this up a little bit if we evaluate 1.528 over 2, that is 0.764 t squared plus 6.94. Now we need to figure out what this arbitrary constant is. Well, it actually doesn't matter what that constant is, as you'll see in a moment when we evaluate this total distance. It really doesn't matter because it will cancel, as you'll see in a second. But we can make this assumption to make it a little easier. We can assume that at time 0, when the driver first steps on the accelerator, that's when we start measuring the distance traveled by the car. We can make that assumption. So if we plug 0 in for t here and here, and 0 in for our s on this side, well, we'll get that 0 equals c. So we can assume that the c is actually just 0 by making this assumption right here. So we have then that our position function is then and then the distance traveled from this point to this point is then going to be the difference between the position function at time 10 and at time 0. Now notice if we plug 0 in here, we just get back 0. So this term here is just 0, so it doesn't really matter. That's because of our assumption right here. And evaluating this, so we can just plug 10 in for t here and here, and when we do that, we get 145.8. You can check that out. And that will have units of meters. And so that is our answer to part B. That's how far the car traveled during the 10-second period of acceleration. And notice I mentioned before that it doesn't really matter what this constant is when we answer part B. That's because if we left a constant in here and here, notice how they would just cancel each other. So it really didn't matter what the constant was. And that concludes this lesson on applications of the antiderivative.